Dividing radical expressions. Typically, when we're dealing with division of radical expressions, we see them in fraction form. We don't see them with a division sign sitting out there, but we need to remember when we see a fraction, a ratio, that is referring to a division problem. So when I see this square root, this radical over this entire fraction, I need to remember that it's really referring to the square root of the numerator and the square root of the denominator. So I could rewrite this one as root 121 over 25 over root 25. And now I can deal with these two individually. Well, the square root of 121 is 11. Square root of 25 is 5. So when I see a fraction with a radical over the entire fraction, I need to remember it's really two separate pieces is one way I can look at it. Do the top separate from that bottom. So number 2, helps to rewrite it. I'm going to rewrite it, or you would always want to if it helps you. Rewrite it as two different cube roots. So I would have the cube root this time of 125x to the 12th over the cube root of 64y to the 9th. So I'm dealing with a cube root this time instead of a square root. Cube root of 125 is 5. Cube root of x to the 12th, x to the 4th, 3 goes into 12 4 times. I go to the denominator. Cube root of 64 is 4. Cube root of y to the 9th, 3 goes into 9 3 times. So I'd have 5x to the 4th over 4y cubed. Looks a little worse in number 2, a little more difficult because I'm looking at a cube root versus a square root. Variables are coming in, but I followed the same process. I'm looking at the numerator and denominator separately. Same idea in 3. I'm going to rewrite it. Root 27a to the 5th over root 9b to the 4th, and then take care of each part individually. 27. All right, that's 9 times 3. So I've got square root of 9 is 3 coming out. That 3's in. Other 3 is in. Square root of a to the 5th. 2 goes into 5 twice. 1 left over. Over. Square root of 9 is 3. A little easier than the 27. Square root of b to the 4th. 2 goes into 4 twice. None left over. And there's nothing else I can do there. I don't have any terms that, oh, I missed that. Correction. I can take out the 3's. I can reduce those two 3's, so my simplified answer would be a squared root 3a over b squared. Missed that to start with, but I could simplify those two 3's. So when I see a fraction inside a radical, I need to remember that I can work the two pieces individually. When I look at the last two problems I have up here, this time they're already split up, where I've got a radical in the numerator and denominator instead of over the entire fraction. Okay. When I look at something like this, I can work them individually or together. Okay. So in a case like this, I can deal with that root 27. There's that 9 times 3 again, and that would give me 3 root 3x. X is staying over root 3. Then those two root 3's would cancel because similar to multiplication, inside with inside, outside with outside. These two 3's are inside. So that would be 3 root x, and that would be all I could do. I just got a 1 underneath there. Now let's look at it a little bit different here. Another way I could look at this problem. A lot of times when I see something down here that doesn't simplify so well, and actually I'm just going to rewrite the problem. So I really can't do anything with that root 3. There's nothing I can pull out of that radical. But I look at the numerical pieces, they're both inside. Wait a minute, 3 can actually go into 27. I can reduce it. So I need to remember that just because I see them separate, they could have also been written together. Like that. Square root of the entire fraction, 27x over 3. This I could reduce. 27, or excuse me, 3 goes into 27 9 times. Still got my x. And then I can do the square root of 9. I can't the x. So a lot of times when I see something that can't simplify on the bottom or in that denominator, I will look and see, wait a minute, can that denominator go into the numerator? If so, I can reduce it. I can think of it two ways. I can rewrite it as a fraction inside, or just remember, hey, wait a minute, these two pieces are both inside, so they can reduce. So I could take that 3 into 27. Let's use that idea here on the last one. The last one I have on the board. So let's see. Cube root of, I can't really do a cube root of 6, so I wish I could simplify that. I can't. So I start looking, hey, wait a minute, can something from the denominator go into the numerator? In other words, can I reduce the fraction? They're both inside the radical, so I can. Let's see, 6 goes into 48 8 times. So I'd have an 8. X squared into x to the 8th would leave me x to the 6th. Y to the 5th and the y to the 14th leave me y to the 9th, and there's nothing left on the bottom. Well, I guess there would be a 1, but nothing that's going to change my overall answer. Now I can look at this. Cube root of 8. Cube root of 8 is 2. Cube root x to the 6th. 3 goes into 6 twice. No x is left over. Cube root of y to the 9th. 3 goes into 9 3 times. No y is left over. So when I'm dividing with radicals, treat them like a fraction that I could reduce. And then go inside with inside. Remember that if you see a fraction, you can look at them independently. Because if that radical is outside the entire fraction, then I'm really looking at that radical of the numerator and denominator independently. The one thing that does show up with division is sometimes I have a situation where I have something that I cannot simplify, like a 5 over root 2. 2 doesn't, I can't even take the 2 into the 5 because number 1, 2 doesn't go into 5 evenly, and number 2, that 2's in the radical, that 5's not. It wasn't the square root of that whole thing. Okay. However, when I have my radicals simplified, I want to make sure there is no radical, square root, cube root in the denominator. When we see a radical in the denominator, we need to rationalize it. So we're going to talk about rationalizing. Rationalizing means that I'm just trying to eliminate the square root from the denominator. I can't do any kind of simplifying, but I can definitely get rid of that square root. The reason we do not want a square root in the denominator or cube root, we'll see, is because when it comes to adding, subtracting, that kind of things with fractions, we need to be able to get common denominators. Those radicals get in the way. So if we end up with a square root in the denominator, our last step would be rationalize. Here's how we rationalize. I've got something I can't simplify. So what I'm going to do is I'm going to multiply numerator and denominator by a root 2. This is going to rationalize, take the radical out of the denominator, because root 2 times root 2 is just 2. I guess technically it is root 4, but the square root of 4 is 2. And then on the numerator, that would just be 5 root 2. So this 5 root 2 over 2 is the same value That's 5 over root 2. This is a rationalized answer, which means no radical in the denominator. I have eliminated the radical that was in the denominator. This is a fraction. On a fraction, I can change the fraction by multiplying the numerator and denominator by the same value, and it doesn't change the overall value of the fraction. So for example, if I have 5/8, if I multiply top and bottom by 2, I get 10/16. So that's an unreduced fraction, but it's the same value as that 5/8. Why did I pick a root 2? Because I'm looking to get rid of this radical. And I know root 2 times root 2 is 2. Again, technically, root 4 would be that 2. So I want to make sure on any division that I'm working with, I don't end up with a radical in the denominator. So let's look at one we can simplify all at the same time. Let's go square root of 25 over 18. Well, 18 and 25, that's not going to reduce. So I'm going to think of it like I did before. Hey, this is really root 25 over root 18. Well, I can do the square root of 25. That's 5. Root 18, it's 9 times 2, so that's 3 root 2. That's all the simplifying or reducing of that I can do. But my final answer, I do not want a radical in the denominator. So now I'm down at this point, I need to get rid of that root 2. To get rid of that root 2, I'm going to multiply numerator and denominator by root 2. I'm not using the 3 root 2. The 3 is not a problem. It's not inside the radical. So in the numerator, 5 root 2. Denominator, 3 is still there. Root 2 times root 2 is 2. Remember, really root 4, which would be 2. So I have 5 root 2 over 6. So that is this solution, or this reduced fraction, rationalized. I've gotten rid of that radical. So anytime I see a square root that cannot be simplified in the denominator, I want to rationalize it and get rid of that square root. When we had these fraction ones up here earlier, I didn't end up in that situation. I didn't end up with a radical still left in the denominator. Sometimes we will. Okay? So let's look at a few more where we just end up with that radical sitting in the denominator. So let's say I've got 15 over square root 5. Looks like I can reduce. I can't because one's inside the radical, one's not. But I need to rationalize it, so I'm going to multiply numerator and denominator by root 5. So that'd be 15 root 5. And then root 5 times root 5, that's just 5. Again, root 25, which would be 5. Now I look at this, it's rationalized, and I actually ended up with something I can reduce. 5 goes into 15 3 times. So that one would be 3 root 5. So sometimes when we rationalize, we end up with a fraction that could still be reduced. We can reduce something. We didn't get that in the first two. Again, I can't simplify this because one's out, one's in. Same thing here. I know I see a 2 and a 6, but the 2's in, the 6 is out. These were both out, right? So I can reduce that fraction. Okay. Main idea, though, still, if I have a radical in the denominator, I do not want that in my final solution, my final simplified answer. I want it rationalized. So that's a case where we're seeing a square root. Let's say we see a cube root. Let's go 8. Now let's go 6 over cube root 2. Cube root up there. All right. I can't reduce the 2 and 6. So I need to rationalize. So I need to multiply both numerator and denominator, this time by the cube root of 4. A little different with a cube root. With a square root, I'm going to multiply it by itself, because that'll give me 25, like in this previous problem. 25, root 25 is 5. That'll give me root 4. Root 4 is 2. If I just put a 2 here, I would end up with cube root 4. Well, I can't do the cube root of 4. I need that perfect cube in there. That means I want 4, because now that's going to give me 6 cube root 4 over cube root 8, and cube root 8 is 2. I need that perfect cube, not a perfect square. So now 2 actually go into 6, so that would be 3 cube root 4. I've got another one that I could end up reducing there. So let's look at a cube root again. Let's say, let's go 7 over the cube root of 5. Can't reduce. I need to get rid of that radical in the denominator. I need to rationalize it. So I'm going to have to figure out what to multiply top and bottom by. I know it's going to be a cube root. And I want just a 5 in there. Right, so 5 cubed is 125. That means I'm going to need to multiply by cube root of 25. That's going to give me the 125 down there I wanted. So I would have 7 cube root 25 over the cube root of 125. And cube root of 125 is 5. So 7 cube root 25 over 5. And now we've got one that doesn't reduce any further. That's okay. Sometimes they will. So you went into 6. Sometimes they won't, but I still eliminated that radical. That's my rationalizing. When we have a binomial, 2 terms in the denominator, changes things just a little bit. Let's say we had 3 over 2 minus root 5. Can't simplify. I need to get rid of that root 5 though. So when I see 2 terms of binomial, I want to use the conjugate. So I'm going to have to do some multiplying to get rid of that radical. The conjugate's what's going to help me get rid of that radical. So 3 over 2 minus root 5. The conjugate would be 2 plus root 5. That would be the conjugate. So it's going to be that middle sign that changes. Here's how the conjugate is going to help us. Remember when we multiply, it's just a distributive property. So a lot of students like to put parentheses around them so then it looks like a distributive property up here. I've got a binomial times a binomial. Starts to look a little more familiar. So let's see, 3 times 2 is 6 plus 3 root 5. Then that denominator. Let's see, 2 times 2 is 4 plus 2 root 5 minus 2 root 5 minus 5. You're going to be minus root 25, which is 5. The conjugate, when we use it, it ends up with 2 radicals here that subtract out. So we'd have 6 plus 3 root 5 over, let's see, 4 minus 5 is negative 1. So anytime I see a binomial, I want to use the conjugate. Get another one with a binomial. This time I'll put 2 radicals down there. Let's go 4 over, let's go root 2 plus root 3. Can't simplify the fraction. I need those radicals out of the denominator. I see two terms. I need the conjugate. So the conjugate of root 2 plus root 3, should have been a 3, would be root 2 minus root 3. I'm going to multiply numerator and denominator by root 2 minus root 3. Again, if it helps you, parentheses around it. And again, sometimes that's nice because you can see just a straightforward distributive property there, 4 times that. Up here, you see a binomial times a binomial. Go. Let's distribute. 4 root 2 minus 4 root 3 over, root 2 times root 2 is 2. Root 2 times negative root 3 is negative root 6. Root 3 times root 2 is positive root 6. And then root 3 times negative root 3 is negative 3, and there's where those two radicals subtracted out. So I'd have 4 root 2 minus 4 root 3. 2 minus 3 would be negative 1. Don't read anything into the fact I got negative 1 in the denominator twice. That's just the numbers I made up here. The key is we're not going to have a radical. We're not always going to have a negative 1. It might be a 5. It might be a 13. But I'm not going to have that radical there. If we were to see something a little different, like a binomial in the numerator, let's go like 2 plus root 5 over 3 minus root 7. Remember, in our simplified form, we don't care if there is a square root sitting in the numerator. We care that there's a square root sitting in the denominator. We need that rationalized, that radical eliminated from the denominator. So when I'm thinking about a conjugate, because I see two terms, my focus is that denominator. I'm trying to eliminate the radical, the denominator, by rationalizing. So the conjugate would be 3 plus root 7. 3 plus root 7, numerator and denominator. The conjugate of the denominator, because that's what I'm rationalizing, not the numerator. So once again, you don't have to, but I think sometimes it is helpful when I get parentheses in there, because then I can kind of see, you know what, I've got a binomial times a binomial. I got some work to do here, and that multiplied out, and a binomial times a binomial. So stuff I've done, I've multiplied binomials times binomials, but they do take a little bit longer than just, say, distributing a 4 like we did back here. So in the numerator, 2 times 3, 6. 2 times root 7 plus 2 root 7. 3 times root 5 plus 3 root 5. And root 5 times root 7 plus root 35. Those are both on the inside. Over. Now I don't see any like terms up there. That's okay. There's nothing I can put together. If there was, I would. I go to the denominator. 3 times 3 is 9. Plus 3 root 7. Minus 3 root 7. Minus 7. There's where those two radicals are going away. 9 minus 7 is 2, so there's that denominator. And, you know, I've just got a situation here where the numerator just did not simplify. I got 4 terms up there. That's okay. You know, if a 2 would go into each one, I'd do it. I can't do anything there. Not the best looking answer in the world, but there's no radical in the denominator. That was my purpose for the rationalizing. So in division or fraction format with radicals, sometimes I'm going to end up with a radical left in that denominator. My final answer needs to be rationalized. Don't want a radical left in that denominator.